Okay, let's simplify this radical. So to simplify it, the first thing I'm going to do is I'm going to apply the quotient property. And what the quotient property says is this. The quotient property says that if the nth root of a and the nth root of b are real numbers, and b is not 0 because you can't divide by b, then for any integer n greater than or equal to 0, the nth root of a over b, the fraction a over b being the radicand, is equal to two separate radicals, the nth root of a being divided by the nth root of b. So we can take fractions that are the radicand and split them up into a numerator and a denominator that has radicals. That's what we're going to use to simplify this. So I notice that there's a fraction as my radicand, and that does not lead to a simplified radical. If you have a fraction radicand, then you know that your radical is not simplified, so you have to use the quotient property to split it up. You'll get the square root of 48 x to the 7th over the square root of y to the 18th. Then we're going to break up the square root of 48 x to the 7th into two radicals using the product property. So that's going to be the square root of 48 times the square root of x to the 7th, and the y to the 18th is just going to stay the square root of y to the 18th. Then I'm going to break this up now. I need to figure out what is a perfect square that's a factor of 48. The largest one is what I need to find, actually. So even though 4 is a perfect square, because the square root of 4 is 2, and it goes into 48, I'm pretty sure there's a bigger one. Now, 9 doesn't go into 48, and neither does, 16 actually does. 16 is a bigger one that goes into 48, and we know that the square root of 16 is 4. And 25, the next one, the square root of 25 is 5. 25 is too large of a number to go into 48, though. So therefore, I'm just looking for 16. That's the number I'm looking for. That's the largest perfect square that is a factor of 48. So I break up the square root of 48 into the square root of 16 times the square root of 3, because 16 multiplied by 3 would give me the 48. The 16 is the factor that I actually need. The x to the 7th, I'm going to work on that by doing a division problem. It's the square root of x to the 7th, so I'm dividing the 7, that's the power, by the index 2. 7 divided by 2 gives me a 3. 3 times 2 is 6. And then when I subtract, I get a remainder of 1. The numbers here play a role in what we're going to get. The 1 and the 6 add up to 7, for instance, and that's how I'm going to break up x to the 7th. I'm going to break up x to the 7th as x to the 6th, 6, multiplied by x to the 1st, because when I multiply those, I add the exponents and I get x to the 7th. I'm going to pretty much do the exact same thing for y to the 18th. So y to the 18th, I'm dividing the power of 18 by the index of 2, and this one goes evenly 9 times. 9 times 2 is 18. The subtraction gives me no remainder, so the square root of y to the 18th is good. I can actually simplify that. So now I'm just going to gather stuff up. I'm gathering, let me see. So the things I'm gathering, I'll gather all the ones that I can actually simplify, like the square root of 16. I know the square root of 16 is 4. 4 is the square root of 16. And the square root of x to the 6. Well, I can simplify that because I can think of a square of a power of x that gives me x to the 6. Namely, if I divide 6 by 2, I'll get x to the 3rd, and that makes me know that if I take x to the 3rd and square it, I will get x to the 6, and since I'm taking the square root of a square, I'll be able to cancel the square root and the square. Now the 3 and the x don't simplify, So I'm just going to leave the square root of 3 and the square root of x alone. So there I have the 16, the x to the 6, the 3, and the x respectively. Then in the denominator, I'm looking at 18 here, and I'm saying, well, I need to figure out what power of y I can square to get y to the 18th. And the answer is exactly 18 divided by 2, the power divided by the index, which is 9. So now I can finally simplify it all the way. I have the 4, which was the square root of 16. Now the square root and the square here will cancel, leaving just x to the third, but because 2 is an even number, the index being even means I need absolute value. The square root of 3 and the x are just that, the square root of 3x. In the denominator, I have the square root of y to the 9th squared. The square root and the square will cancel, leaving me the absolute value of y to the 9th. Once again, because that is a square root of a square, I need the absolute value. Now, can I get rid of these absolute values? Well, no, I can't, because 3 is an odd number, meaning the actual sign of x to the third depends on x itself. If x is negative, then x to the third will be negative, and the absolute value won't be x to the third, it'll be the opposite. Same for y to the 9th. Because 9 is an odd number, I cannot get rid of the absolute value. So this is the answer that we will give for the first one here. We'll make a fraction bar, and the top will be 4 times the absolute value, and there's the button for the absolute value of x to the power of 3, and then that's multiplied by the square root of 3x. Yeah, and in the denominator, I'll have the absolute value, so I'll hit the absolute value button once again, of y to the power of 9. And hopefully it accepts the offering. Yes, it likes that. So that's how you simplify this kind of radical here. That's how you simplify. All right, let's take a look at this last one here. So for this last one, we're doing exactly the same thing. I'm going to move a little bit more quickly here. So for instance, I'm breaking it up into the square root of 27b to the 15th y to the 19th divided by the square root of, oh, actually, we shouldn't break this one up right away. What we should do right away is actually simplify on the inside. I didn't realize these have the same base. Since they have the same base, I can actually just do the division by subtracting their exponents, so that this actually becomes 27b to the 15 minus 4. 15 minus 4 makes b to the 11th. You subtract the powers when the bases are the same and you divide. And then this one would be y to the 19th minus 3. 19 minus 3 is actually 16. So we can simplify it that way first, actually. That'll make our lives easier, because then there's no fraction at all. And then we just split it up into the square root of 27 times the square root of b to the 11th times the square root of y to the 16th. And then you do each individual one. So you need a perfect square that goes into 27. I think the winner is 9. The square root of 9 is 3. I think that'll be the largest perfect square. That's a factor of 27. As a matter of fact, 27 I'm going to write as 9 times 3. So that's the square root of 27 taken care of. Then for b to the 11th, well, I'm taking the 11 and dividing it by 2. 5 is how many times it goes in, and the remainder is 1. So I'm going to break up b to the 11th into b to the 10th times b to the 1st, b to the 10th times b to the 1st, because b to the 10th times b to the 1st will give me b to the 11th. And then for the y to the 16th, doing the same kind of thing here, dividing 16 by 2, and it turns out that goes 8 times. 8 times 2 is 16, so there's no remainder. So y to the 16th gets to stay y to the 16th. Now I'm going to simplify all the ones that can be simplified. The square root of 9 is 3. The square root of b to the 10th. Well, it turns out that in order to do that, we rewrite it as a square of some power of b. And the power of b I squared to get b to the 10th is b to the 5th. 10 divided by 2. Still got the square root of b there. And the b to the 16th, what I have to square to get, or not b, but y to the 16th, what I have to square to get y to the 16th is 16 divided by 2, y to the 8th. So now I can simplify fully. I have the 3, so the 3 is good, but the square root of b to the 5th squared, the square root and the square cancel, leaving me the absolute value of b to the 5th. And then there's also the square root of b. And then for the y, the square root of y to the 8th squared, I can cancel the square root and the square, leaving the absolute value of y to the 8th. Now let's see if we can get rid of any of these absolute values. And let's actually see if we can simplify any further here. Oh, I can move them around to put the 3 in front. It's already there though. And then this one, because the power is odd, b to the 5th. I don't know if b to the 5th is positive or negative. It actually depends on if b is positive or negative. So I can't get rid of the absolute value for the b to the 5th. On the other hand, the y to the 8th, I know y to the 8th is positive because when you raise a real number to an even power, it's always positive, and therefore the absolute value of y to the 8th is y to the 8th. The things that I have to keep underneath the radical, there's only one of them. Oh, I forgot this here. I forgot the square root of 3. So there's a square root of 9, which is 3, but there's also a factor square root of 3 that I missed there. So I still have to have the factor square root of 3 in the answer. So not only do I have the 3 and the absolute value of b to the 5th and the absolute value of y to the 8th, but I also have the square root of b and the square root of 3, that square root of 3 that I neglected from the 27, because 9 times 3 is 27. And that square root of b, or the square root of 3b, has to stay under the radical. So this will be my final answer here. This will be what it'll accept. It'll accept 3 absolute value, 3 times the absolute value of b to the 5th, b to the power of 5, times y to the power of 8, times y to the power of 8, and then multiplied by the square root of 3b, square root of 3b. All right, folks, that is section 8-2.